Have you ever read a headline claiming a new study proves coffee is good for you, only to see another one the exact same week saying it's basically poison?
Oh, yeah. It happens all the time. I
Yeah,
mean, one day it's this miracle cure for everything, and then, the next day it's a massive health hazard.
right. It is completely enough to give you whiplash. But today, for this deep dive, we're decoding the secret mathematical language that turns those raw numbers into, well, those flashy headlines.
It's an incredibly important topic.
It really is, because this is the language that dictates how major decisions are made. In medical research, in business, public policy, and yeah, in the news you read every single day. Once you know how to read the data, you really start seeing the matrix behind everything.
It truly is a modern superpower. Like, in a world of absolute information overload,
Yeah.
being able to critically look at data and understand not just what the numbers say, but what they're actively hiding, it gives you an incredible edge.
Definitely. But before we can start finding those hidden patterns in the data, though, we have to know how to simply describe what is right in front of us,
Yeah.
right?
Exactly.
And I guess the absolute foundation here is understanding exactly who or what we're actually looking at.
Yeah, the most fundamental distinction you can make in any kind of quantitative analysis is between a sample and a population. It sounds really simple, but getting this confused is where a whole lot of bad science
Oh, I
starts.
bet.
So a population is everyone, every single person or thing in the group you want to study. And if you actually have data for every single one of them, the resulting number is called a parameter. It's a true actual value.
But I mean, testing literally everyone on Earth or even just in a single city, that's usually impossible.
Right, way too expensive and time consuming.
So you take a smaller group, you sample 100 people to guess what a million people might think.
Exactly. And the number you get from that smaller sample is called a statistic. It's an estimate. So everything we do in statistics basically revolves around using that smaller sample to make a highly educated, mathematically sound guess about the larger population.
Right. And the sources actually gave a perfect little memory trick for this, which I loved. It goes, samples yield statistics and populations yield parameters.
That is a great way to remember it. S and S, PNP.
Yeah. So once we have that sample, we obviously want to summarize it. We want to find the middle ground, like what is typical for this group. And we usually rely on the mean, the median, or the mode.
The famous three, most people are pretty familiar with the mean, your classic average, where you just add everything up and divide by the number of scores. It's basically the balance point.
Right, the classic average.
Yeah. And then you have the median, which is the literal middle number when you line everything up in order, like 50% is above it, 50% is below it. And the mode is simply the most frequently occurring score.
But knowing the middle is really only half the story, isn't it? You also need to know how spread out the data is, the dispersion.
Oh, absolutely.
Because think about it. If everyone in a class scored exactly a 75 on a test, the mean is 75. But if half the class got 100 and the other half got a 50, the mean is still 75. But the reality of that classroom is vastly different.
Yeah, it's a completely different teaching challenge. And that is exactly where the standard deviation comes in. It's kind of the workhorse of statistics.
How so?
Conceptually, it just tells you, on average, how far each individual score deviates from that middle mean. So a small standard deviation means everyone is clustered tightly together. A large one means the data is spread far and wide. You also have the range, which is just the highest score minus the lowest score, but standard deviation is the big one.
Okay, let's unpack this, because you can have all that math totally right, but still get it completely wrong in the real world, depending on the kind of data you have.
Oh, definitely.
Let's say you survey your friends on a new movie, and the options are strongly disagree, disagree, neutral, agree, strongly agree.
Right, a classic survey scale.
Exactly. And you assign those options the numbers 1 through 5. You do the math, and you get an average, a mean of 2.5. Does that average actually mean anything in the real world?
This is a fantastic point. What you are describing is an ordinal variable. These are categories that have a clear order, but the distance between them isn't mathematically precise.
Because it's just words. Yeah.
Exactly. The distance between neutral and agree isn't exactly one unit of anything real. It's an emotion.
Right. It's just a feeling. It's not like measuring inches or dollars.
Yeah. So calculating a mean for ordinal data is a bit of a mathematical illusion. I mean, the calculator spits out a number, 2.5, but mathematically you cannot have a 2.5 on a scale of distinct human feelings. It completely lacks a true practical interpretation. You have to match your statistical tool to the reality of your data.
That makes a lot of sense. So if the mean is our standard go-to for finding the center of continuous data, what happens when things aren't perfectly balanced? Because we always hear about the bell curve, where everything just sits perfectly in the middle.
The normal distribution. It is a beautiful thing in statistics. When data is normally distributed, the mean, median, and mode are all the exact same number, sitting perfectly in the center.
Like a perfect hill.
Exactly. And it follows this magic empirical rule.
Right.
68% of all your data will naturally fall within one standard deviation of that mean.
Yeah.
And about 95% falls within 1.96 standard deviations.
What nature isn't always that neat, is it? Often, data leans really heavily to one side. We call that skewness.
Yes, skewness. When the distribution is not centered, it has this tail that stretches out to one side. And this is exactly where relying purely on the mean gets incredibly dangerous.
Right, think about American incomes. Like, most people's incomes might cluster around a median of, say, $67,000. But then you have billionaires. Elon Musk, Jeff Bezos, Bill Gates. They are such extreme outliers on the high end that they pull the mathematical average way, way up.
That is what we call a positive skew. The tail points to the right, toward those extreme high values, and it creates a deeply misleading mean.
And a negative skew would be the opposite.
Exactly. A negative skew is where the tail points to the left. The textbook uses the example of age at death. Most people pass away at an older age, but tragic early deaths create this long tail stretching down to the smaller numbers on the left.
So going back to the income thing, if Bill Gates walks into my local pub, on average, everyone inside is a billionaire.
Yeah, mathematically, yes.
But the median income of the room didn't change a single cent.
What's fascinating here is that this isn't just some quirky math puzzle, It is an ethical obligation for researchers. When data is highly skewed by those billionaires, researchers absolutely must use the median instead of the mean to represent the center.
Because if they don't, they are basically lying to the public using accurate math.
Exactly. The math is perfectly correct, but the story is totally false. And instead of using standard deviation to measure the spread in those cases, they use the interquartile range, or IQR.
What does that do?
It just looks at the middle 50% of the data. So it completely ignores those extreme billionaires pulling the strings at the ends.
Ah, that's smart. Okay, so we can describe a single group accurately now. We can spot the outliers ruining our averages. But life is really about how things connect. How do we measure if two different variables are actually related?
This is where we move from univariate analysis, which is looking at one variable, to bivariate analysis, looking at two at the same time, and eventually multivariate, which is more than two.
Right. So let's take a school board election from the chapter. We want to know if a voter's gender is related to which candidate they prefer, let's say Patel or Chen, because these are categorical variables, like you fit into a distinct box. We use something called a cross-tabulation.
Yeah, a contingency table. It is essentially a grid. You put gender on one axis, the candidate on the other, and you just see how the frequencies stack up in the intersecting cells.
Okay.
It lets you quickly see if, for example, male voters are disproportionately leaning toward one specific candidate compared to female voters.
But what if our variables are continuous sliding scales, like, say, hours spent studying versus the actual score on a test? They aren't just boxes anymore.
For continuous variables, you look for correlation. And the most common measure for that is Pearson's R.
Pearson's R?
Yeah. It gives you a single number between negative 1.00 and positive 1.00.
Oh.
And you usually visualize this with a scatter plot.
Oh, I've seen those. Just a bunch of dots.
Exactly. Each dot on the graph represents one person's score on both variables. If the dots cluster really closely around a straight diagonal line, you have a strong relationship. If they look like a random cloud of confetti, you have no correlation at all.
Okay, here's where it gets really interesting. With Pearson's R, you said it goes from negative 1.00 to positive 1.00. If a correlation is negative, like say it's a negative 0.89, does that mean it's a weak relationship just because it's below zero?
That is a very common misconception. The positive or negative sign only tells you the direction of the relationship, not the strength.
Oh, really?
Yeah, the absolute value is what actually matters. A correlation of negative 0.89 is exactly as strong as positive 0.89.
So what does the negative actually mean in real life then?
It simply means the variables move in opposite directions. Think of outside temperature and hot soup sales.
Okay.
As the temperature goes down, soup sales go up. That is a strong negative correlation. The variables are highly connected. They just operate like a seesaw.
I love that seesaw analogy. Okay, so let's say we find a strong correlation in our sample of 100 people. We draw our scatter plot, we see the trend. But if we only surveyed 100 people, how do we know our result isn't just a total fluke? How do we actually prove it's true for the whole population?
Well, this requires taking a massive leap, which brings us to inferential statistics and hypothesis testing. At its core, this is simply a mathematical reality check.
And it all starts with the null hypothesis. I love this concept. The null hypothesis is essentially the universe's default setting of nothing to see here, right?
That's a perfect way to put it.
It's the assumption that there is no real difference or relationship between your variables in the real world, and whatever trend you just found in your sample is purely random, dumb luck.
Yep. The burden of proof is entirely on the researcher to prove the universe's default setting wrong. And to reject that null hypothesis, you use specific statistical tests depending entirely on the shape of your data.
Right, you can't just use one master formula for everything. Let's break down how we choose. If we have those categories, like our school board election grid, we use a chi-square test.
Yes, chi-square. Conceptually, a chi-square test takes the grid of your actual observed data, and it compares it to a hypothetical grid of what the data would look like if everything was totally random. It calculates the difference between reality and random chance.
And the text mentions something about degrees of freedom for that.
Yeah, it's just a quick calculation. Rows minus 1 times columns minus 1. That helps the formula adjust for how big your grid is.
Got it. But what if we are comparing averages, like in an experiment? Say we take a group of teachers, give half of them a workshop on using new technology, and the other half gets no training at all. We have two groups, and we want to compare their average tech fluency scores.
For comparing the means of exactly two groups, you use a t-test. It analyzes the two averages and the spread of the scores to tell you if the difference between the groups is large enough to be real.
But experiments usually have more than two groups. What if we had a workshop group, a self-guided tutorial group, and a control group?
Once you hit 3 or more groups, the t-test is out. You have to use ANOVA, which stands for Analysis of Variance.
Wait, if ANOVA basically does the same thing, why not just do a bunch of t-tests back-to-back? Like test group A versus B, then B versus C, then A versus C.
Think of running a statistical test like rolling a 20-sided die.
Okay, Dungeons and Dragons style.
Exactly. Every time you run a test, there is a small chance you will roll a critical failure like a fluke result caused by random error. If you roll that die just once, getting a failure is pretty rare. But if you run 15 different t-tests back-to-back comparing every single group to every other group, you're rolling that die 15 times.
Oh, I see.
Yeah, you are practically guaranteeing that you will roll a false result just by pure chance. ANOVA solves this by letting you roll the die just once to test the entire group simultaneously.
That makes perfect sense. It's about containing the risk of making an error. But what if things get really complicated? What if we aren't just looking at one thing causing another?
That is where regression basics come in. Specifically, multiple regression. It is one of the most powerful tools in research. Multiple regression allows you to see how several different variables affect an outcome, all at the exact same time.
Okay, take college entrance exams. Say a researcher wants to know if taking an expensive test prep course actually increases scores. But in the real world, you know that a student's GPA, their parents' education level, their age, all of that probably also affects that score.
Yeah, exactly. If you just compared test prep to no test prep, the result would be hopelessly tangled up with those other factors.
Right.
Multiple regression allows researchers to mathematically control for all those other variables. It isolates the test prep time. It holds GPA and age mathematically constant, so you can see the specific naked effect of just the prep course on the exam score.
It levels the playing field, so you're finally comparing apples to apples.
Precisely.
So let's say we run our multiple regression. We isolate the variable, and the computer spits out that our results are statistically significant. We defeated the null hypothesis. We're done, right? Time to publish.
Not exactly. And this is where a lot of headlines get it so wrong. We have to face the so what test. We have to separate statistical significance from effect size.
Because when a result is statistically significant, all it literally means is that the result is probably not a fluke.
Right. We measure this with a p-value. The standard cutoff, which we call alpha, is usually 0.05. That simply means there's only a 5% chance that the results could be produced by pure random chance if the null hypothesis were actually true.
But because we're playing with probabilities, we can still make errors.
Oh, absolutely.
A type-by error is a false positive. We claim we found a massive breakthrough, but it was just a weird sample. At a 0.05 level, we are openly accepting a 5 in 100 chance of making this exact embarrassing mistake.
And then a type 2 error is a false negative. The cure was real, the relationship was absolutely there, but your specific sample just missed it, so you failed to reject the null hypothesis.
So what does this all mean for the data? Let's assume we didn't make an error. We have our statistical significance. If my sample size is massive, say I surveyed 100,000 people, couldn't a totally meaningless, microscopic, tiny difference show up as statistically significant just because of the sheer volume of data?
If we connect this to the bigger picture, you have hit on the exact flaw of modern data reporting.
Yes.
With huge samples, statistical significance is practically mathematically guaranteed.
Huh.
A difference of 0.01% will flag as mathematically significant because the sample is so huge the computer knows it's not a fluke. But in the real world, who cares about a 0.01% difference?
Which is exactly why we need effect size.
Precisely. Effect size measures the actual magnitude of the difference. Imagine researcher 1 tests a new exercise program for depression and finds a 2-point drop in depression scores. Researcher will build 2 tests of vitamin and finds a 5-point drop. Both are statistically significant, but they use completely different questionnaires with completely different point scales.
Yeah, you can't compare a 2 on one test to a 5 on another. It's apples and oranges again.
So we use standardized metrics for effect size like Cohen's d for t-tests to translate their different point systems into one universal language. By the way, for Cohen's d, 0.2 is small, 0.5 is medium, and 0.8 is large.
And there are others too, right?
Yeah, like Kramer's V for chi-square and eta square for ANOVA. It standardizes the data so we can definitively say the exercise had a medium effect, but the vitamin had a large effect. It answers the crucial question, is this finding big enough to actually care about?
Which brings us to the final hurdle. We've done the math, we found a significant result, and we've proven a large effect size. The numbers are pristine. But before we implement a change in the real world, we must step away from the calculator. We have to look at practical significance.
Because data does not exist in a vacuum. A statistically sound finding can be practically useless. There are 5 key considerations when looking at practical significance outlined in the text. First, you have to do a cost-benefit analysis.
Right. Say you have a computerized math program. It raises test scores significantly, with a huge effect size. But it costs $5 million to implement, and it has instructional time for reading and science. Practically, it's a failure.
Exactly. Second, you must consider the crucial difference. Sometimes an effect size is mathematically tiny, but practically immense. In medical research, if a drug only saves 3 lives out of 100,000, statistically that is a minuscule effect. But practically, that is 3 living human beings. It is a crucial difference that demands action.
Wow, yeah. Third is acceptability to the client. If the students absolutely despise that new computerized math program, it doesn't matter what the pilot study numbers say. They will eventually burn out, develop negative attitudes toward math entirely, and your intervention will backfire.
The fourth consideration is where things get really thorny. Public and political acceptability. The chapter takes a look at housing-first models for homeless individuals.
The research on these programs is actually fascinating. The sources show the data works beautifully. Giving housing directly to people gets them off the streets and statistically saves taxpayer money by drastically reducing emergency room visits and jail time.
The data is incredibly solid, but it often lacks political support. Why? Because, as the sources point out, a segment of voters feels very strongly that public funds should not go to individuals they personally deem undeserving. We're not taking a side here, but it just shows how the data can be mathematically perfect, yet still hit a wall of public perception.
Absolutely. And finally, the fifth consideration, ethical and legal implications. Think about the research into psychedelics like psilocybin and LSD.
Right. There's compelling quantitative evidence they might be an incredibly effective treatment for cluster headaches, which are often described as the most painful condition known to humanity.
But legal restrictions and international drug classifications make it nearly impossible to use them systematically or prescribe them in most places.
This raises an important question about the limits of quantitative data alone. You could spend years doing the most perfect, mathematically flawless multiple regression analysis. You can control for every variable, prove massive effect size, and completely reject the null hypothesis.
Right.
But it can all get shut down because of funding or politics or laws. A truly great researcher cannot just be a mathematician. They must also be a sociologist, an ethicist, and an economist. Numbers are just a tool. They are not the complete solution.
That is a very powerful way to look at it. We have covered a lot of ground today. We started by drawing the line between our population and our sample. We learned to watch out for billionaires wildly skewing our averages and hiding the reality of the data.
Yeah. Always check the median.
Always. We measured relationships using correlations and visualized them with scatter plots. We took the leap of inference to test the null hypothesis, choosing our tools carefully to avoid false positives. And finally, we weighed the sheer math of significance against the messy, unpredictable reality of human cost, politics, and ethics.
You now have the foundational tools to look at a statistic and actually ask the right questions, rather than just taking the headline at face value.
So I want to leave you with this final thought. The next time you see a statistic in a news article confidently declaring that variable X absolutely causes variable Y, ask yourself, what are the invisible variables they didn't control for in their regression? Was the sample size so massive that the finding is mathematically significant but practically meaningless? And when they declare a crucial difference, who is actually benefiting from it? The numbers rarely lie, but they only ever tell the part of the story you force them to tell.